There are also all of these informal aspects of a conference where, like, we had a gathering of all of the women at the conference last night, and it was really nice, and I made some new friends. So that's the kind of stuff that you would miss if you weren't in person.
Welcome, everybody. My name is Sebastian. Thanks for coming to my talk. So my talk is going to be about how to make code reusable. What techniques do we have in C++ to make code reusable? And crucially, towards the end of my talk, what techniques we have but shouldn't use to make code more reusable. But more about that in a while. So we as programmers, we are pretty lazy. And that's a good thing. We typically don't want to repeat ourselves. In fact, this is so important to us that we gave this a fancy name and called this the DRY principle, the do not repeat yourself principle. And that's not just our laziness, of course. That's an important aspect of software development, because if we don't repeat ourselves, then our software becomes easier to maintain, right? We have to fix bugs once, ideally. So I want to look at some of the strategies we have in C++ to share algorithms and data, and want to give some guidance on when to use which. And why this talk? Well, we have a lot of tools in C++, and we keep inventing new tools and give long talks about them at these conferences, but we have relatively few talks about when to use which tool. And as part of my job, I'm interviewing a lot of junior developers, and that interview, of course, involves a bit of programming and refactoring specifically. And so this is a bit about this talk is a bit about the things that I see people do that I would not recommend. So let's start with a little motivating example. Let's say we have a super clever layout algorithm. This layout algorithm can center widgets vertically. And my slides are in HTML, so you know that centering stuff is pretty complicated. And these widgets, they have complicated shapes, so for simplicity, we want to lay out them by their bounding boxes. So we might have a simple algorithm like this. So comment about my code samples, they are all pretty short, and some of them use our open source ThingCell library, that's the TC namespace, but that should all be pretty familiar to people familiar with the range standard library. Okay, so this algorithm might look like this. It's called vertical center. It takes a container of those widgets, and then it just extracts their bounding boxes, creates a vector of them. Then some magic happens that we are not interested here. And then afterwards, it outputs all those rectangles again and places all those widgets. Okay, that's simple enough. Now, let's say we have a slightly different problem somewhere else in our code base. We have rectangular bitmaps. And we also want to center them vertically because we know, well, because that looks very good. And we also know that we have that code somewhere else in our code base. So we want to reuse it. So what do we do? So we have a bit of code. We want to center bitmaps. We have, let's say, an array of those 3 bitmaps. Let's give us some more context, some data structures. So we saw that the widget, they have bounding boxes, they have rectangles, we can place them, but the bitmap is completely different, right? A bitmap is just an array of bytes, and it might have a width and or a height, maybe even only one of them, to interpret those bytes. It does not have a rectangle, for example, right? You can render bitmaps at some location, but it doesn't have a rectangle. Okay, now what can we do? What do I see people do? And I'm showing the least bad solution because I don't want to show too much wrong code. So people intuitively have the idea that they can use templates. And that's, of course, a good idea because templates are always the right solution in C++, right? And here, well, let's say the thinking stops. And they continue and do something like this. So they say, hey, I make this a template. What else do I have to do so I don't have to touch my code at all? So they build a little contraption like this. They build like this widgety interface on top of the bitmap. Semantically, that doesn't make much sense, but it makes stuff work. So of course, now we can reuse that algorithm. We don't even have to look at it. That's going to work. So we've achieved our goal. We solved our problem. We can tell our boss, hey, we are done. That was super fast. But getting things done is not the only metric we have, right, when we do software engineering. It's one aspect, but it's not the only one. We want to write software that is easy to maintain, that we can still understand in 10 years. So what happens here? I think what happens is that because of our laziness, people usually see that they can reuse code. But then their first instinct is they don't want to change anything. They want to reuse it as it is. So that's a bit our laziness taking over, right? Because understanding code, especially code other people have written, or sometimes code that you have written in the past, is super hard. But writing code is super easy, and writing code is super fun. That's why we are in this business, right? We love writing code, we love getting stuff done, we love seeing the results of what we've programmed. So making stuff work is fun. And we have so many tools to make things work. We could have solved this problem with inheritance, with variants, with optionals, and I've seen all those solutions. But the more tools we have, the more bad ways there are to make things work. And what they all have in common is that they're all like fitting the square peg in a round hole, right? But if code reuse is critical for writing software that's easy to maintain, then it kind of counteracts the purpose when we start building contraptions to reuse code. Then we have suddenly more code that we have to maintain instead of less. An interesting aside, I wanted to generate that image using the image generator in the same style of all my other images, and they were unable to do so, because when I told them I want to have a round hole and a square peg, they could not do it. Their Bayesian priors always took over, and the peg always fit the hole. So that was an interesting limitation. So what do we have to do? And I know this sounds trivial, but in practice it turns out it's not that trivial. So when we want to write easy to reuse code, we have to generalize from the algorithms we have already programmed. So we have to understand our own problem. What is it we are trying to achieve? We have to understand the solutions we already have. What do they do in detail? And crucially, we have to be able to talk about both of these things in terms of the underlying problem, and not in terms of C++ jargon, right? And only then can we try to generalize algorithms. Then we can try to figure out what parts of the solution can we maybe extract, generalize, reuse in other contexts. So how can we extract the small generic algorithms, the small building blocks that our project should have? And of course, we can always only generalize if we have actually more than one use case for algorithms, right? Otherwise, our generalization will generally be wrong. So let's look at how this looks in that simple toy example. So I said we have a bitmap, doesn't have a rectangle. And then we look at our algorithm. And we see the algorithm essentially, as the first step, extracts rectangles. It extracts rectangles from our input, does stuff on rectangles, and then outputs rectangles. So it's natural maybe to rewrite it that way, right? We should analyze this deeper, because the algorithm is centering stuff vertically. Why does it need rectangles? Isn't this just operating on intervals, maybe? So there's still, always good cause for thinking about the algorithm. What are you actually doing? Is that the right thing we are doing? Should we be doing this completely differently? But let's say we're working on rectangles. Then we should rewrite it like that. We should extract that. This is the core of the algorithm we've actually programmed. The input is a range of rectangles. It should work for any range of rectangles. For simplicity here, I said that the range should return rectangle references. Now this is easy to reuse. You could just calculate some initial rectangles, reuse it. This is a much better solution. That has only minimal requirements. It's more generic, easier to use, and has much less dependencies. It only needs rectangles, and I would assume any part of our code base that does anything like layouting stuff knows about rectangles, right? So that's the first point. When we have an algorithm that we want to share, but we want to share it with different data, then generic functions are the tool C++ gives us to do that, right? Templated functions. And we write good templated functions by extracting the required operations on our inputs, and we write them down as concepts. And Bjarne Strostrup has a paper that was titled How to Write Good Concepts, where he says, well, if you are inventing concepts for your functions, then be careful that you don't always come up with the minimal required operations, because you then might end up with a lot of ad hoc concepts that are maybe kind of similar and overlapping, but all a bit different. What he says is you should come up with fundamental and complete concepts that maybe make sense in your code base. So an SDL example would be a regular type, for example, right? In our case, it might be a rectangle, a range of rectangles, for example. But in order to do that, we have to analyze the algorithms, we have to analyze the code we have, think about them again, and again, we can't generalize from single use cases. And I want to revisit that quickly. When we want to write good generic functions, then they have to be customizable, so they stay powerful. And there are a couple, like 4 main techniques, I think, to customize generic templated functions. Because the problem we have is that we have client code that calls a generic function, and we want that generic function to call back into our client code, right? So the first technique we have is dispatching to global function overloads. So here I stay like in the same problem domain. We're calculating positions for things. And we do that for different things, for different widgets. And what we do is that the algorithm, when it has calculated results, it calls a global place function, and we have to provide that function for all input types. Now that's a very simple technique. It has important advantages, I think. It doesn't require us to write any boilerplate code. It's very simple. The compiler does everything for us. It's non-intrusive. We can provide function overloads for all kinds of types that we don't control, even for integers. But it also has some disadvantages. For one thing, the contract might not be quite clear to the caller. There's nothing in the interface to indicate you need that method, so you have to document it. And it's also a little bit inflexible, right? So these two things, our place items function and this global overload, they are kind of tied together. That's not ideal. But still, it's something we do pretty often in the SDL. There are global overloads for std size, std begin, std end, specifically because we wanted to override them for C-style arrays, for example. And we use them in generic code all the time. So let's say we have a more generic algorithm that just calculates stuff and we don't have any assumptions on what the user is doing with the outputs we are calculating. Let's say copy if, for example, would be such an algorithm. So the SDL has a simple concept that's the output iterator. But the output iterator is kind of a weird concept because it's not really a minimal concept. It has this increment operator. I don't know historically why we came up with that, but that's the way it is. But I would say the minimal concept is just a function object, right? So if we have algorithms that calculate stuff and want to output that, one very elegant way is to just provide an output function where you can stuff the results into. So these are just called. And here we can do anything. We can do an allocation if we wanted to have an allocation. We can process the results immediately, draw them, whatever. So that's better, of course, than allocating a vector of the results and returning that, which would be unnecessarily pessimistic if we don't need the allocation. Here, in that case, you might say, well, that's maybe a bit over-engineered. It looks like we could just return a transform range, for example, because it looks like we are just calculating a range from the inputs. But there are other algorithms where that would not be the case, where we would calculate results piece by piece. Let's say you have, again, a layout algorithm where the result for the 5th item depends on the 4 previous calculations you have made. So it's more convenient to just output results as you calculate them. And then again, you let the caller decide what to do, store them somewhere or process them live. Now we can take this further, and the STL, of course, has many different functions, function objects. There are predicates, there are projections, all kinds of things. And we know this from the STL. But having a lot of those on one function object, that can get kind of hard to understand, right? So we can do something else. That's the last one. We can group things together in what I would call something like the command pattern. So let's say we change problem domain a little bit. We're doing string matching. So we're doing dynamic programming. And dynamic programming is a very convenient algorithm, can be used in a lot of different contexts, and it has a lot of customization points. So right here we are trying to calculate the minimal number of insertions and deletions between two strings. Our dynamic programming algorithm would take those two ranges and would calculate if we match the left side, if we skip the left side match or skip the right side. We could customize the type of the costs. We could customize the initial costs that we start with. When we have a custom cost type, we need a custom cost comparator, and finally we need a function to calculate the cost of the next step. And instead of passing 4 arguments, we could just group them together in one object and pass that. So generic algorithms, generic functions need clear requirements. We want to express them in well-known concepts, and then they reduce dependencies, they become easy to reuse, and they stay flexible, customizable through customization points. And then there are always the right answer in C++, right? By the way, if you have any questions in between, you can always also interrupt me and just ask a question. Any question so far? Yeah. So this was about sharing algorithms with different data. Now we can also have a case where we have both code that we want to share and some data. Our dynamic programming example, for example, is such a case, right? Because we have an algorithm and we always have some data that every instantiation will have because we always calculate some matches. So we have a shared algorithm that produces some data. And data and code together, that's what classes are invented for, right? So we can rewrite the dynamic programming thing as a class. So it would be a class dynamic programming. We would customize it, template it with the type of the derived class. This is where the customization points go, and the costs and the initial costs. We have some shared data, that's the matching. And here we can even provide a little common interface because those matches would typically be iterated back to front because that's just how we calculate them. So we make that easily accessible and then have the shared algorithm. So of course you have seen that before. That's the curiously recurring template pattern, right? Our actual implementation will be derived from dynamic programming. Now we call it string match, and we just put all the customization points that we have there. So we are using compile time polymorphism to build new types, right? Inheritance is here just an implementational detail. We just want to reuse code. So we use inheritance out of convenience, not as a big design decision. That inheritance is typically not visible to the user, but we can get a generic interface, shared algorithms, shared data here in the templated base class, and can customize their operation somewhat. Now we can have templated derived classes, that's CRTP. We can of course do the inverse as well, right? We can have templated base classes. That's also very practical for code sharing. So we might have, let's say, a child process, and we want to pipe data to the child process. And we want to do that in different ways. And those different ways we customize through the base class. For example, we could do the piping asynchronously or synchronously. Via the base class, we could also write different implementations for different operating systems, right? Here again, the inheritance is purely an implementational detail to build a new type out of code pieces. And when do we use which? When do we use CRTP? When do we use templated base class? That's also a decision that we make more out of convenience than out of big design questions, right? We can ask ourselves, who owns the data? Do we need to access that data in our customization points? Then it's more convenient to put data in base classes. Is there a specific initialization order we need to follow? And we just ask ourselves, what creates less friction, less casts? And that's probably the preferred implementation. And now, of course, when we have templated base classes, templated derived classes, we can always also have something in the middle, the mixin class. And we use that when we have functionality that we want to add to otherwise unrelated types. So here, a little silly example. Let's say again we have UI widgets. They all have a mouse move function. We have the familiar widgets, buttons, drop downs, etc. And we want to add a very annoying functionality to some of them, namely that they beep whenever the mouse is moved. And we do that by selectively adding that beep modifier to some of those classes. Okay, so that's a lot of template. That's probably something where a lot of you said, yeah, I know this, I do this. But what about the other tools we have? And I think I mentioned them in my abstract. What about inheritance? What about virtual functions? What about std_variant? I use them all the time. And sometimes it looks like I'm using them to reuse code. And I see people do that in my interview task. And I don't think we should use them to reuse code. Because code reuse is an implementation decision. We don't want to repeat ourselves. It's a decision we make out of convenience, right? We have different parts of our code base that coincidentally want to call the same piece of code, but we don't want to tie those pieces of our code base together, right? They're unrelated, they should stay unrelated. So we have generic functions, we have generic classes, for example, to achieve that. We reuse in unrelated contexts, we don't want to tie them together, and like I said, out of convenience, not as a big design decision. But runtime polymorphism, that is completely different, right? Runtime polymorphism is a decision that if we introduce that into our code base, if we model our solution with runtime polymorphism, then that has important implications for the future of our code base. It makes things harder to change, maybe, in the future. It ties things together. Everything in that class hierarchy, for example, is suddenly strongly coupled to each other. All these types now share base classes. They share a common interface. That interface must have the same meaning for all types that participate in your class hierarchy. If you have common implementations, that implementation must also be correct for all these types. So that's what I mean when I say this is an important design decision that has implications for our future, right? So there's a well-known talk, and there should be a YouTube link here. We don't have that. There's a YouTube link here, usually. You see that, I don't see that. That's fine. Okay, you see that. So there's a very famous talk by Sean Parent about runtime polymorphism. And there's the better known, shorter version is called, Inheritance is the root base class of all evil, right? And in there he talks about polymorphism. And he has that very famous quote, the requirement of a polymorphic type by definition comes from its use. There are no polymorphic types, only polymorphic uses of similar types. And what he means here is that there's no inherent property in things in our code base that says these things should have a polymorphic relationship, right? There's nothing inherent. There's this example we use in textbooks, hey, there's an animal and sheep derives from animal, etc. There's nothing that is inherent in those types. Only if we ever have usage in our code base that needs to talk to all animals and doesn't care which one, then we need to use polymorphism. Because polymorphism has important disadvantages. We get types of different size. They require heap allocation. That requires lifetime management. That implies an inefficient indirection, encourages shared ownership, and that leads to synchronization issues. So I want to look at 3 different ways that we can implement and use runtime polymorphism, depending on the use case we have and depending on the constraints that we have in our code base. So here's maybe the simplest way. Here's the canonical way. You have a drawing application. So this is PowerPoint with a bit of ThinkCell. So your application is an empty canvas. That's your application. The user can add anything to that. He draws shapes, he draws charts, whatever the user wants, right? And they're all the same from the point of view of your application. So you treat them all the same. They all have a huge shared interface. They will all be rectangular. They all have a dirty flag. They can all be clicked and then build a context menu. Those context menu items can be clicked. They can all draw themselves, and many, many more things. So your application will look a bit like this. You have this container of heap allocated objects, and you talk only through that polymorphic interface. Objects can be selected, grouped, resized, deleted, saved, loaded. You get the point, right? So that's the textbook example of inheritance, and where I think it's the right solution, right? Now let's look at a slightly different example. We want to build cool user interfaces, or more specifically, we want to build user interface library. And that user interface library has one important feature. It's that all the widgets can be automatically layouted. They have constraints, so when the text changes or when the dialog is resized, then they will be automatically layouted. So we might have code like this. We have widget-based classes that have some virtual interface. They have a minimum size, they can add constraints to a solver, they can be placed, and then we have the typical buttons, text boxes, whatever widget you come up with. And we have a base dialog class that has some polymorphic usage. When the dialog is resized, it's clear what should happen. We have to collect all the constraints over all the widgets in the dialog, solve them, and place them again. Okay, but how do we want to use this? How should our client code look? Our client code wants to look like this. We have an instance of a dialog that has maybe a text box and a button, but these two have an identity. They are very specific text boxes and buttons. They're not anonymous objects in some container. I want to add an event handler to that button. That button wants to know what text is entered into a specific text box. These things also have a very simple life cycle, right? I don't want to heap allocate them. They will just be constructed when the dialog is constructed, and they will be destroyed when the dialog is constructed. Very simple. Now, we could do something like this. We could add a virtual visitor function that is called by the root class, and then whenever it wants to iterate over all the widgets, it calls this. Well, that's not a very good solution, because it means we have to repeat ourselves, right? We have to repeat all the members that we have created somewhere else. That is very error prone. That's bound to fail at some point, and there's no compiler that can warn us about this. So we did something else. In our library, we used intrusive containers. There's, for example, a boost intrusive implementation. Intrusive containers have interesting properties. Intrusive containers don't take ownership of the objects you add to them. They're called intrusive because they are intrusive in your data structure. So when we use an intrusive list and you add an object to that list, that object has to carry around the 2 pointers it needs to be in that list. So there isn't even any allocation to your list. So this is how that could look. The dialog widget inherits from this guy some boost intrusive base class that carries around this data structure, these 2 pointers for a linked list. And the dialog has an intrusive list of all the widgets. All the widgets register themselves automatically, and when they're destructed, they will also deregister themselves automatically. Now the dialog can do polymorphic usage of all those widgets, but at the same time, we have very clear ownership of those objects. They're all, like we wanted, owned by our individual dialog implementation. They all have an identity, and this mixed bag of widgets doesn't concern our client code. That client code still looks the way we wanted it to look. Okay. Now, the last aspect of polymorphism is what Sean Parent presents in his talk. I used to call that Sean Parent style polymorphism until somebody told me this is called external polymorphism. So what is Sean Parent talking about in this talk? He has another use case. He's also talking about documents and objects. What he wants to have some document that contains objects that can be drawn for the purposes of this example. We draw a document by drawing each individual object. But the main properties that he wants to have is that this should be very easy to use polymorphically with different types, and it should be easy to extend by users. So here you see he's just emplacing back a 5, a string. How's that going to work? So typically what we expect here to see is classic maybe polymorphism. You allocate a unique pointer of some wrapper for that integer that derives from some common base class, and you create some wrapper for the string, etc. And then you deal with all these unique pointers. But he says, I don't want this. I want to hide the polymorphism from the user. This is how the user code should look. How can we make this happen? And this was the solution. So he has this object, and this object takes anything. It has a generic constructor taking anything, and then it internally creates a unique pointer of something. And this unique pointer of something is a virtual base class. So we hide the polymorphism inside that object type. So here we have a unique pointer to a concept. The concept has a virtual draw function, and what we actually allocated was this thing. So again, a generic class that can take any type T and store any type T and implement that virtual draw function. So okay, so far we have something that just takes anything and allocates it somehow. So how does the drawing work? We have a draw function on the object that forwards to our virtual implementation of the draw function, and that virtual implementation forwards again to a global overload. We have seen that before. So if we switch back to the client code, it just looks like we want it to. And all that we have to do is provide these global overloads of draw that you see at the top that we can provide for any type, for integers, for strings, type we don't control. And the user doesn't have to fiddle with any other kind of smart pointers, etc. So that's a very clever solution, I think. So we use runtime polymorphism when, as a precondition, we actually have polymorphic usage of stateful objects. If our objects are not stateful, not really objects, are they? No, we don't need polymorphism at all. And there are different techniques. So if we have interchangeable objects, we use the classic style of owning a pointer to a base class. If we have objects with identity and some polymorphic usage, we can use intrusive containers. And if extensibility is our focus, then we can use this hidden polymorphism, the Sean Parent style. Okay. Now, whenever I give talks, I like to bring examples of what I did wrong, or we did wrong. In this case, I think I didn't do it. Because, well, everybody does mistakes, right? And you learn from mistakes. So here's an example of when we use polymorphism and shouldn't have. Because this was 20 years ago. We started programming 20 years ago. Object-oriented programming was all the rage, so we did it everywhere. So here's again our little user interface. Things are selected, and you see those little circles. You see drag handles that the user can click and drag, right? These little white circles. So what we initially did was that whenever the data model changed, whenever the selection changed, we would collect UI objects. So everything here that is clickable, every single drag handle, would be created as its own individual object. So our application looked a bit like this. When our data model would be updated, we would go over all the selected shapes and create drag handles for every little corner. Later, we would get maybe a mouse move call. This mouse move would go over all these UI objects we had created. Each one implements mouse move. Each one would check hey, is the mouse over myself? In that case, I store the state that the mouse is hovering over me. And then later, we would get a draw call. And again, that draw call would go over all the UI objects, and they would all draw themselves, and every one of them would ask itself, do I remember correctly that the mouse was hovering over me? And in that case, I have to use a different texture. Now, I said we use runtime polymorphism when we have stateful objects. So how many objects of all of these have state, actually, at any one time? There is actually only one of them, because the mouse can only hover over one of them. So we have created an enormous amount of objects that didn't have anything to do, and they didn't have any state. And we realized this after a while, a couple of years, and the final solution was much simpler. We don't have any objects anymore at all. The mouse move doesn't do anything, just sets dirty maybe, and then we can do everything in the draw function. Whenever something wants to be drawn, we just check, is the last mouse position I have over myself? In that case, I draw myself with the hover texture. Otherwise, I use the normal texture, and I'm done. No objects, no runtime polymorphism, just a visitor, if you want. That was much simpler. Now, the last aspect of a design feature that I wanted to touch. State variant. How do we use state variant, and how do we abuse state variants sometimes? So variants are awesome. We use variants to combine types into new types all the time. That is very easy. That's what they're there for, right? So here, let's say we have a function that would search an online image database. And that can return a list of results, or it can return an error message when something went wrong. So we tie those two things together. These are unrelated otherwise as types, but they have, what ties them together is the semantics of that call. They can occur together because they can both be outputs of the search image call. And now, of course, the cool thing of variants is that we can so easily do different things, whatever, depending on what actual content the variant has. So when we have an error message, we want to show an alert. And when we have results, we want to display those results, of course. But there's a certain danger in this because it is so easy to use. And it's so easy to extend. We might search a different image database in the future. That's no problem. We just add something to our variant, add something to our visitor, and we're done. Extending like inheritance hierarchies, that can be pretty hard, right, when they get large. But this is very easy. But if you don't pay attention, and you do this a while, and suddenly your application evolves, you might run into problems. And that's what happened. Here, maybe originally we had one visitor that, well, processed the output and did stuff. Our application inevitably grows more complex. Suddenly we have one visitor that downloads the results. We have another one that just downloads thumbnails for the preview. And maybe then we figure out, oh, in search and new image database, we need to authenticate for those databases as well, or for one of them, maybe. So we have yet another visitor somewhere else in our code base. Now, what happened? What did we do wrong? What have we invented or reinvented? We have invented a polymorphic type by accident. We shouldn't have programmed this. This is now horrible to change, because you have to find all these locations and add related code to all of these code locations. We probably should have written it like this, in hindsight. Okay, so that's just a short aspect of the danger of evolving variants. So that leads me to my conclusion, right? If we want to have code that is easy to reuse, then we should start building our own generic library of the components that you find useful in your code base, and that maximizes code reuse. Design abstractions, we have to choose very carefully. And it turns out, as I've hoped to show in the examples of what went wrong, these different abstractions, polymorphism, variants, visitors, they are interchangeable, but they don't have the same costs. So when we have made design changes in the past, then we should sometimes revisit those choices. Because our code might have evolved, our application has evolved, maybe the choices we made in the past would not be the correct choices if we thought about them again now. Okay, thank you very much. Now I'm open to your questions. Any questions? Okay, everybody has the same opinion anyway. That was one way this could go. Okay, then thank you for coming. Thank you for your attention.